Mars has become the default dream of humanity's future red deserts, domes on the horizon, footprints in iron dust. But what if we've been aiming at the wrong world all along? What if the best place for humanity's next great leap isn't the cold, airless plains of Mars, but a distant moon wrapped in a thick golden sky, where rivers flow, rain falls, and chemistry itself is alive? Titan, Saturn's largest moon, doesn't look like a second Earth at first glance. It's frozen, dimly lit, and smells hypothetically like fuel. Yet beneath that alien surface lies something extraordinary, an environment that quietly solves many of the problems that make Mars so hostile to long-term human survival. Titan has a real atmosphere. It shields against radiation. It overflows with carbon-based resources, the raw ingredients of industry, energy, and civilization itself. In many ways, Titan is less a barren rock and more a world paused mid-creation, waiting to be unlocked. Colonizing Titan would not be easy, but neither is colonizing Mars, and Titan may actually offer a more stable, sustainable future once we get there. If humanity is serious about becoming a multi-world species, we may need to stop asking which planet is closest and start asking which world is built to last. If ideas like this are how you think about the future, you'll want to stay connected and subscribe to Evolvex, where big questions meet bold possibilities. Titan has a real atmosphere. One of the most overlooked yet decisive advantages Titan holds over Mars is its atmosphere. Titan is wrapped in a dense, nitrogen-rich blanket with a surface pressure of about 1.45 bar, slightly higher than Earth's own atmospheric pressure. This means Titan already possesses something Mars lacks almost entirely: a genuinely protective sky. The thickness of Titan's atmosphere shields the surface from harmful cosmic radiation and burns up small micrometeorites before they can strike the ground, dramatically reducing long-term health risks for human settlers. In planetary terms, Titan feels less like an exposed outpost and more like a world that actively defends its surface. This atmospheric density also transforms how humans could physically exist on the surface. On Titan, a human would not need a pressurized spacesuit to prevent explosive decompression. Instead, survival would require an oxygen supply and extreme thermal protection due to surface temperatures near -179 degrees Celsius. The difference is subtle, but revolutionary. Engineering habitats, vehicles, and daily operations becomes far simpler when pressure is not constantly fighting to escape every seal and joint. The presence of a thick atmosphere turns Titan from a hostile vacuum into an environment that can be managed rather than merely endured. Mars, by contrast, exists on the edge of space itself. Its atmospheric pressure averages around 0.006 bar, less than 1% of Earth's. This paper-thin atmosphere offers almost no protection from radiation and does little to slow incoming micrometeorites. As a result, long-term human presence on Mars would likely require habitats buried beneath meters of soil or rock to reduce radiation exposure. Mars does not merely challenge human survival, it continuously erodes it, demanding constant technological intervention just to keep people alive. The engineering implications are enormous. On Mars, stepping outside without a fully sealed, pressurized suit results in unconsciousness within seconds and death shortly after. On Titan, however, atmospheric pressure alone would not be the killer. This single factor reshapes everything from construction methods to emergency response planning. When comparing the two worlds, Titan's atmosphere stands as a quiet but overwhelming argument that long-term settlement may depend less on proximity and more on planetary protection. Radiation exposure is one of the most serious and unavoidable dangers of long-term space colonization, and this is where Titan quietly outperforms Mars by a wide margin. Titan is protected by a dense, nitrogen-rich atmosphere that is thicker than Earth's, which absorbs and scatters high-energy cosmic rays before they reach the surface. While Titan does not possess its own strong magnetic field, its atmosphere alone provides substantial shielding, reducing radiation levels to values far closer to those experienced on Earth than on Mars. This natural protection dramatically lowers lifetime cancer risks for human settlers. Saturn's magnetic environment also plays a partial role in Titan's radiation safety. Although Titan spends significant time outside Saturn's magnetosphere, there are periods when it passes through regions where charged particle radiation is reduced. More importantly, studies from the Cassini mission showed that Titan's thick atmosphere is the dominant factor in limiting radiation at the surface, making it one of the safest solid bodies in the outer solar system from a radiation standpoint. This combination makes surface-level human activity far more feasible than previously assumed. Mars presents the opposite scenario. The planet lost most of its global magnetic field billions of years ago, leaving its surface exposed to solar and cosmic radiation. Its extremely thin atmosphere offers minimal shielding, allowing high-energy particles to reach the ground almost unhindered. Data from NASA's Curiosity rover show that radiation levels on the Martian surface are significantly higher than those aboard the International Space Station, posing serious long-term health risks for astronauts and settlers alike. Because of this radiation environment, any sustained human presence on Mars would require habitats built underground or heavily shielded with regolith to reduce exposure. Surface living would be impractical for extended periods. On Titan, however, the atmosphere makes surface habitats viable without extreme shielding, fundamentally changing how a colony could function. This difference is not cosmetic. It affects architecture, psychology, health outcomes, and the long-term survivability of a civilization beyond Earth. Titan has enormous chemical resources. Titan is unique in the solar system because it is rich in complex chemistry on a planetary scale. Its surface hosts vast lakes and seas composed of liquid methane and ethane, some larger than Earth's Great Lakes. Above them, a thick atmosphere drives an active organic cycle in which hydrocarbons form high in the sky and literally rain down onto the surface. This makes Titan less like a barren moon and more like a frozen world overflowing with raw chemical potential, the kind of environment early industrial civilizations could theoretically exploit. What makes these resources especially important is their versatility. Methane and ethane are not just fuels. They are foundational feedstocks for industrial chemistry. On Earth, similar hydrocarbons are used to produce plastics, synthetic materials, solvents, fertilizers, and energy storage compounds. Titan naturally contains carbon, hydrogen, and nitrogen in abundance, the three elements most critical for building complex molecules. For a future colony, this means less reliance on constant resupply from Earth and more potential for true industrial self-sufficiency. Mars, in contrast, is chemically sparse. Its surface is dominated by iron-rich minerals, basaltic rock, and fine dust, giving the planet its red appearance. While Mars does contain water ice and small amounts of carbon dioxide in its atmosphere and soil, it lacks readily accessible carbon-based compounds. Complex organic chemistry is rare and fragile, and any large-scale industrial use of carbon would require energy-intensive extraction or synthesis processes. In practical terms, Mars offers very little of the chemical foundation that modern civilization depends on. This difference has enormous implications for long-term settlement. Carbon is the backbone of fuels, construction materials, electronics, medicine, and manufacturing. Titan has it everywhere, locked into lakes, skies, and soil, waiting to be refined. Mars, by comparison, is a world of metals and stone that demands constant technological effort just to create basic organic materials. If civilization is defined by chemistry as much as by shelter, Titan looks less like an alien wasteland and more like a frozen industrial treasure vault. Energy is easier to store on Titan. At first glance, Titan seems like a terrible place for energy production. It receives only about 1% of the sunlight that reaches Earth, making solar power far less effective than on Mars. However, energy generation is only half of the equation. Energy storage and stability matter just as much. and this is where Titan quietly excels. Titan's environment is saturated with chemical energy in the form of hydrocarbons, particularly methane and ethane, which exist naturally as liquids on the surface. These compounds represent an enormous, readily accessible energy reserve that can be stored indefinitely without loss. Methane is especially valuable because it is already a proven high-performance fuel. On Earth, methane combined with oxygen is used as rocket propellant due to its efficiency, controllability, and clean combustion. On Titan, methane is abundant, and oxygen could be produced through electrolysis of water ice imported or extracted locally. This creates a powerful chemical energy system that supports transportation, industry, and emergency power storage. Unlike solar energy, which fluctuates constantly, chemical fuels offer predictability and long-term reliability. Nuclear power further strengthens Titan's energy advantage. Extremely cold environments are well suited for nuclear reactors because excess heat can be dissipated efficiently, improving system stability and safety margins. Small modular nuclear reactors could provide continuous base load power for settlements without dependence on weather or daylight. Titan's lack of dust storms also means that any supplementary solar infrastructure would not face the gradual efficiency loss seen on Mars, where panels must be cleaned or replaced regularly. Mars highlights the contrast. While it receives more sunlight than Titan, its energy systems are constantly threatened by dust. Titan is easier on the human body than Mars. Gravity is often framed as one of Mars's strongest advantages over more distant worlds, but when examined closely, the difference is less decisive than it appears. Mars has a surface gravity of about 0.38 g, while Titan's gravity is much lower at roughly 0.14 g. Earth, by comparison, sits at 1.0 g. While Mars does offer higher gravity than Titan, it is still far below the level known to preserve long-term human health. Bone density loss, muscle atrophy, and cardiovascular changes observed in astronauts occur even in microgravity mitigation environments, suggesting that Mars's gravity may not be sufficient to fully prevent these effects. Because neither Mars nor Titan provides Earth-like gravity, colonists on both worlds would likely rely on artificial gravity solutions. Rotating habitats, either on the surface or in orbit, are widely considered the most practical method for maintaining long-term human health. Regular exercise regimes and ongoing medical adaptation would also be necessary regardless of destination. This reality weakens the assumption that Mars's gravity alone offers a decisive health advantage, since the infrastructure requirements end up being similar in both environments. Titan's lower gravity does, however, introduce significant engineering benefits. Reduced gravity makes it easier to construct large-scale structures with less material stress, enabling expansive habitats, domes, and industrial facilities that would be more challenging to build on Mars. Structural supports can be lighter, spans can be wider, and construction energy costs are reduced. Over time, this could allow Titan settlements to grow larger and more efficiently than comparable Martian colonies. Lower gravity also dramatically reduces the energy required for space launch. Titan's escape velocity is far lower than Mars's, meaning spacecraft need significantly less fuel to reach orbit or travel onward through the solar system. This makes Titan an attractive hub for resource export, scientific missions, and deep space exploration. When combined with Titan's abundance of chemical fuels, low gravity becomes a strategic advantage rather than a liability. Terraforming. Terraforming Mars has long been portrayed as humanity's most achievable planetary transformation. Yet current science paints a far more daunting picture. Mars lacks sufficient accessible carbon dioxide to thicken its atmosphere to Earth-like levels, even if all known reserves were released. Worse, the planet lost its global magnetic field billions of years ago, allowing solar wind to steadily strip away its atmosphere. Any artificially thickened air would continue leaking into space, demanding constant planet-scale maintenance over thousands or millions of years. Titan presents a radically different scenario. It already possesses a thick, stable atmosphere dominated by nitrogen. the same base gas that makes up most of Earth's air. This atmosphere is not rapidly escaping into space, giving Titan long-term atmospheric stability that Mars lacks. Instead of building an atmosphere from nothing, terraforming Titan would focus on modifying temperature and chemistry. A fundamentally different challenge with potentially more permanent results. The central obstacle on Titan is extreme cold. With surface temperatures around -179 degrees Celsius, water exists only as ice. However, models suggest that if Titan were warmed sufficiently, liquid water could exist on its surface beneath the existing nitrogen atmosphere. This makes Titan unusual among non-Earth worlds. Its main limitation is temperature, not atmospheric collapse. While warming an entire moon is no small task, the end state would be comparatively stable once achieved. In essence, Titan resembles Earth frozen in time, rich in chemistry but locked in deep cold. Mars, by contrast, is a world that has already lost much of what made it Earth-like and continues to erode. Terraforming Mars means fighting physics indefinitely. Terraforming Titan means changing conditions on a world that can actually hold on to the results. That distinction may matter more than distance or difficulty in the long run. When looking at the big picture of humanity's future beyond Earth, the choice of where to settle depends on the long-term goals. Mars is ideal for early exploration and a handful of research bases. Its proximity to Earth allows for faster missions, simpler resupply, and easier political coordination. For short-term objectives, it is the natural first step in off-world colonization. Titan, however, offers a very different opportunity. Its thick atmosphere shields against radiation. Its surface is rich in hydrocarbons and other chemicals essential for industry. And its nitrogen-rich air allows for surface operations with fewer engineering constraints. Titan is not just habitable in theory, it provides the foundation for a self-sustaining civilization that could endure for millions of years. Unlike Mars, which feels like a temporary outpost exposed to cosmic hazards, Titan could become a true new branch of human society, one capable of growing, expanding, and maintaining industrial and scientific systems on its own, even if the environment is extremely cold and distant. For anyone fascinated by the future of human exploration and the potential of worlds beyond our own, the story of Titan is a reminder that the most promising opportunities are not always the closest ones. Like, comment, and share your thoughts. And subscribe to Evolvex for more insights into humanity's next great frontier.